take it away.
Thank you. Thank you for the introduction as well as for the invitation. So today I will talk about a recent joint work with Viktor Ginzburg and Basak Gurel. So let's start. Okay. So here is the background question. How much Floer theory knows about dynamics beyond periodic points? So in this work, we focus on, among the dynamical features, we focus on topological entropy. And here's the question that we try to answer. Can one detect the topological entropy of a Hamiltonian diffeomorphism using the data coming from Floer theory? As for this data, we are using barcodes, and we define the notion of Floer-theoretic entropy, which we call barcode entropy, and then we compare it with topological entropy. So I will come to that, but first let me recall the definition of topological entropy, a definition of topological entropy. So XT is a compact metric space, and let's take a continuous map from X to X. So for each natural number K, we define another metric on X. So given X and Y, we look at the orbits under F up to iteration K, and then take the maximal distance. And given epsilon positive, let's say as epsilon K be the maximal number of pairwise epsilon separated points with respect to this metric dk. Then the topological entropy is given by this equation, given by this. So first we fix epsilon, then look at the exponential growth rate of S epsilon K, and then send epsilon to 0. So this number here, topological entropy, measures orbit complexity of the map F. So here is an example. Let's take from circle to circle the doubling map. Then topological entropy is equal to log 2. And we are working with, in this talk, logarithm is base 2, so it's equal to 1. Now, it's not hard to see this from the definition. You just write the points in binary expansion, then multiplication by 2 erases the first digit. Then for epsilon less than, let's say, 1/2, one easily finds 2 to the k points that are separated with respect to dk. Now, more examples slash some results, theorems. So on closed surfaces, topological entropy of autonomous Hamiltonian diffeomorphisms is 0. And this is not true in higher dimensions. So in number 2 and 3, we compare periodic orbit growth and topological entropy. Number 2 is a result by Katok. On closed surfaces, topological entropy is bounded from above by growth rate of periodic points. So this is not true in higher dimensions. It's easy to construct a counterexample. Namely, you pick a map which has positive topological entropy and product it with an irrational rotation, either of circle or torus. Then the resulting map does not have any periodic points, but it still have positive topological entropy. Okay. Now the Floer-theoretic entropy, barcode entropy. Here first the setting. So all of these are throughout the talk. So M omega will be closed monotone symplectic manifold. L will be closed monotone Lagrangian with minimal Chern number at least 2, and phi is going to be a Hamiltonian diffeomorphism. So all maps and manifolds are C infinity. This is because we are using, I'll come to this, but we are using Yomdin's theorem, and that requires C infinity. Now, so L, phi, and M as above, let's the epsilon L, phi, L be the number of bars in the barcode of the Lagrangian Floer complex of length greater than epsilon. So I will briefly talk about barcodes in 5-10 minutes. For now, let me tell you how do we use these numbers. These numbers give us a lower bound for the number of Hofer-stable intersections. Namely, like if you take, let's say, a Hofer small perturbation of L, small in the sense, then from stability of barcodes, we get the first inequality here. In addition, if L tilde is transverse to phi of L, then number of bars is bounded from above by number of intersections, number of generators of the complex. So if you don't see the middle term here, so left-hand side, B epsilon is a lower bound for the Hofer-stable intersections. So I write the same thing here. B epsilon is a lower bound for the Hofer-stable intersections. Now we have two versions of barcode entropy. First, the relative one. Barcode entropy of phi relative to a Lagrangian L is the following. We first fix epsilon, then look at the exponential growth of B epsilon as k goes to infinity, and then send epsilon to 0. So this number here, h sub epsilon, it increases as epsilon goes to 0. So the limit exists, but it can be a priori infinite. We will see that this is actually finite in a second. Now the second version of barcode entropy, as in the Lagrangian case, this time set B epsilon phi to be equal to the number of bars of length greater than epsilon in the barcode of the Hamiltonian Floer complex of phi. So remark, this is important for our results. So like in this work, we work with all free homotopy classes of loops, meaning that this complex is generated by all fixed points of phi, not just contractible orbits of the flow. And here is the second definition, absolute barcode entropy. As in the Lagrangian case, we fix epsilon, look at the exponential growth of B epsilon, and then send epsilon to 0. Here's a small note. Absolute barcode entropy of phi is equal to the entropy of identity times phi as an Hamiltonian diffeomorphism of the twisted product relative to the diagonal. So this just follows from the identification of two complexes. Okay. Now some formal properties. So I compare them here with topological entropy. So bar entropy is invariant under conjugation, and also phi and phi inverse have the same barcode entropy. I mean, this is just because barcodes have this property, like B epsilon have this property, and we have the same thing for topological entropy. So now I'm looking at number 2, 3 of topological entropy. It is additive plus homogeneous. We don't have, or at least like a priori, we don't have these properties for barcode entropy. Number 2 and 3 just follows from the definition. We have inequality because we are taking the upper limit in the definition. And finally, the fourth point is that the relative version is lower semi-continuous in the Lagrangian with respect to the Hofer metric. All right. Now, main results. Our first result is that the relative barcode entropy is bounded from above by topological entropy. So as a result, we get that the barcode entropy is finite because topological entropy is finite for smooth maps. And as a corollary, we get the same inequality for the absolute version. So we just like apply theorem A to identity times phi relative to the diagonal. And we use the additivity of topological entropy. Entropy of identity is 0, so we get corollary A. So these are our results, like when we bound barcode entropy from above by topological entropy. Now we will try to do the other inequality. So let me recall a definition.
Erman,
compact.
Yeah. Can I ask a question? The properties you put on the previous slide, the one right before this, yeah, for the barcode entropy. I mean, do these follow more or less in a straightforward way from the properties of barcodes and the definition, or are they
exactly?
Sorry.
Exactly.
Okay.
Exactly. They follow from definitions.
Okay. Okay. Thanks.
I mean, 2 and 3 from definitions. 1 and 4 are properties of barcodes. Yeah. Like the fourth one is stability of barcode with respect to the Hofer perturbations, and one, yeah.
Okay. Okay. Thanks.
So I said this. Now, a definition. A compact invariant set K of phi is called locally maximal if it admits a neighborhood such that K is the maximal invariant set in there. So every point in the complement, either in positive or negative iterations, leaves U. So in this definition, like this definition has nothing to do with being hyperbolic, but we work with locally maximal hyperbolic sets. So I just wanted to emphasize that here. So here's our theorem B. On such sets, like locally maximal hyperbolic sets, the topological entropy is bounded from above by the barcode entropy. As an example, for a locally maximal hyperbolic set, one can take Smale's horseshoe. And here's a nice property of locally maximal hyperbolic sets. On them, topological entropy is equal to the periodic orbit growth rate. So in general, like there is no such relation. Like anything can happen. Left-hand side might be 0, right-hand side might be infinity, or vice versa. Or like right-hand side might be 0, left-hand side might be non-zero. But on locally maximal hyperbolic sets, we have the equality. And here is a nice result by Katok. On closed surfaces, all entropy is coming from such sets. So when you take the supremum over locally maximal hyperbolic sets, you recover topological entropy. Now, as an application, our previous results, and together with Katok's results, we get equality in dimension 2. So for Hamiltonian diffeomorphisms of closed surfaces, bar entropy is equal to the topological entropy. And the proof is corollary A, here's corollary A, theorem B, and Katok's results. So let me say the following, like corollary A and theorem B, they hold in any dimension. So we can squeeze this bar entropy between these two in any dimension. But in dimension 2, like we have Katok's result that gives the equality. And here is a remark. In theorem B, and also as a result in C, it is essential that the Floer complex is generated by all fixed points or all intersections in the Lagrangian case. I mean, this is just because in theorem B, so the periodic orbits in K, and they don't have to be contractible. So we need to count all of them. All right, these are our main results. Let me go over previous works. So the first group is like study of topological entropy for Reb flows, symplectomorphisms, and contactomorphisms. Frauenfelder and Schelling, they work on symplectomorphisms, show that under some conditions, topological entropy of a symplectomorphism is positive. Maccarini and Schelling, I'm just going to go through them briefly. Maccarini and Schelling, they work in the Reb setting. They generalize like previous positive entropy results for geodesic flows in this paper. Alves himself and like with many collaborators, they extensively study entropy of Reb flows. Like there are many papers in here. So one example is that with MyVes, they show that on higher dimensional spheres, there's a contact structure such that every red flow has positive topological entropy. And Dahin then works in the setting of contactomorphisms. Now I'll move to the Hamiltonian setting, but before that, let me make a small comparison. So in this setting, the entropy is captured by growth of the Floer homology. In the Hamiltonian setting, the Floer homology does not grow, like it doesn't depend on the Hamiltonian diffeomorphism. So we detect topological entropy by looking at like less robust features of the complex, and these are the barcodes. Okay, now I want to go through some results in dimension 2. There are more results on the next slide, but before I go through them, let me say the following: like all of these results in dimension 2, topological entropy is equal to the barcode entropy. So all of these results also hold for the barcode entropy, but like we cannot recover any of them at the moment, just looking at the barcodes. First result is due to Humilier. He shows the following: let L be an equator. That means L divides the sphere into two equal areas. There exists a constant such that for all Hamiltonian diffeomorphisms of the sphere, the upper limit of the normalized Hofer distance between L and phi to the k is bounded by some constant times topological entropy of phi. For instance, if left-hand side is non-zero, topological entropy is non-zero. And Hanetsky, so in this result, the genus of the surface is at least 1. We take a non-contractible Lagrangian, and for all positive number, there exists another Lagrangian, which is Hamiltonian isotopic to L, such that every Hamiltonian diffeomorphism that takes L to L sub n has topological entropy at least n. So it is clear from the statement, but let me say it, like here, the topological entropy is detected at phi. So you don't look at the iterations of the map. Two more results. This
Sorry,
one is
Erman,
by Chor and my.
So when so this result by Vincent Millier, as far as I know, the left-hand side is that limb soup divide of the Hofer distance divided by k. There are no. It's a major open conjecture whether that's open question whether that's 0 or not, right?
Yes. Yeah. As far as I know.
Examples.
So it might be always 0.
It might always.
You're saying that, right?
It might always be 0, but maybe it's conjectured to be positive. There's something called the diameter conjecture in Hofer geometry, which says maybe that left-hand side is positive. That's just a comment I was going to make about that in the call. So what I guess what it says is that to get positive, to get the left-hand side to be positive, you need topological entropy. So you need a complicated map.
Yep.
Okay.
Okay, the result by Chor and Maives, they show that for each positive number, there exists now, like the genus is at least 2. For each positive number, there exists an open and dense subset of Hamiltonian diffeomorphisms. This is with respect to the Hofer metric, such that on U, topological entropy is at least n. And finally, a result by Alves and Maives, they show that in dimension 2, there's no requirement on the surface. Topological entropy is lower semi-continuous, again, with respect to the Hofer metric. So I repeat this here. All of these results hold for barcode entropy as well, but we cannot recover them at the moment.
But you said something about the lower semi-continuity of barcode entropy, so that does not imply the Alves-Midas theorem?
No, let me go
You just said
there.
it's,
So this is for relative
okay, so
barcode entropy, and it is in the Lagrangian, not in the Hamiltonian, not on the diffeomorphism. This is lower semi-continuous in the Lagrangian.
wait, so it should hold for the diffeomorph. I mean, if you look at h bar of phi without the L, it's still true, no, with respect to the whole metric on phi. Is it not? Or maybe it's not.
No, but I think I didn't understand the question.
It's okay. Okay, no, it's okay.
But this doesn't. I mean, this doesn't imply.
Okay, I understand. Yes, you're right. Okay.
These are the results. Now, I would like to briefly go through barcodes. The barcodes and persistent modules, they're introduced to symplectic geometry by Poltarovich and Shalukin, then it became a widely used tool. So in this work, we use the framework developed by Asher and Zhang. So before I go through that framework, let me tell you our setting. So let's suppose that like L and phi of L intersects transversely. So the Lagrangian complex is generated by all capped intersections over the universal Novikov field over F2, and it's filtered by the action. By this filtration, I just mean that the Floer differential strictly decreases the action. So I don't mean that the complex is filtered over lambda. Just differential strictly decreases the action. So here, I don't rate them like in the complex, but both the differential and the action depend on other data like Hamiltonian complex structure, etc. So we implicitly make these choices. Now a definition by Asher and Zhang. So a lambda basis for our complex is called a singular value decomposition if, so under the differential, alpha I goes to 0 and gamma j goes to eta j. And we also require that sigma is orthogonal in the non-Archimedean sense. So let me recall what orthogonal means. So a subset of the complex, a finite subset of the complex is called orthogonal if for every linear combination, the action is equal to the maximal action of the summons. For instance, so we are not working in the setting, but let's assume that Novikov field is the trivial one. And let's say that all capped intersections have distinct actions. Then beta I is orthogonal if and only if their actions are distinct. Or similarly, let's take two members of the complex. If action of beta 1 is strictly less than action of beta 2, then beta 2 comma beta 1 plus beta 2 is not orthogonal. When you sum these two, the action strictly decreases. So roughly speaking, we don't want cancellations when we take the linear combination. Okay. Now, given a singular value decomposition, the barcode B, capital B, of the complex is defined in the following way. It is the multiset formed by finite bars. We take the action difference of gamma and etas together with some infinite bars, and the multiplicity is equal to the dimension of the homology. So this dimension is equal to the number of alphas and gammas and etas here. So what is the so if we multiply the number of finite bars by 2 and add the number of infinite bars, we get the dimension of the complex. Here's the theorem, a couple of theorems by Asher and Zhang. So first of all, the complex admits a singular value decomposition. Its barcode, this multiset, it only depends on phi and L. So it makes sense to talk about barcode of L and phi of L. And we have the Hofer stability. So when you make a Hofer small perturbation, the number of bars do not decrease much. Okay. Here is a note. So far, like we assumed that L and phi of L intersects transversely, but by continuity, one can define barcode of L and phi of L even if they don't intersect transversely. But if they do, then number of bars is less than number of generators, intersections. And the second note is that so the dimension of the homology does not depend on the Hamiltonian diffeomorphism. So if our barcode entropy is non-zero, then the growth comes from these finite bars. So in the epsilon, we always count infinite bars, because infinite is more than epsilon, but the growth does not come from there. Okay. Now, I will sketch the proofs of theorem A and theorem B. Theorem A says that relative barcode entropy is bounded from above by topological entropy. Here is one of the ingredients of the proof, Yomdin's theorem, which says the following. Let's take a C infinity diffeomorphism of our manifold and a compact submanifold. And then the volume growth of n under iterations, the upper limit, is bounded from above by the topological entropy. So because of this theorem, because we are using this theorem, we assume that everything in the setting is C infinity. Now back to the proof. Suppose that this barcode entropy is non-zero, otherwise there's nothing to prove. And let's take a number between 0 and the barcode entropy. So for simplicity, let's, instead of phi to the k, I'll write L to the k. And we choose an epsilon and a sequence going to infinity such that B epsilon L comma L to the ki is bounded from below some constant times 2 to the ki alpha. So such an epsilon and ki exists because alpha is chosen so that it's less than the entropy. Now by Yomdin's theorem, let's make the following observation. It suffices to show that volume of L to the ki is bounded from below by some constant again times 2 to the ki alpha. These constants do not have to be the same, but I mean the constant shouldn't depend on ki, but as long as we can find this, we are done. So we will try to estimate the volumes of L to the ki.
Is there an assumption on the dimension, the dimension of n in Yomdin's theorem?
No. For any n, for any dimension, this holds. And actually, if you take the supremum of left-hand side over all dimensions and all submanifolds, you recover topological entropy. So step 2, we call this step Crofton's inequality. It is similar to Crofton's equality. So in this step, there are no Lagrangians or Hamiltonian diffeomorphisms. This is a general setup. So let's take a closed submanifold of M and a compact manifold B. And let's say psi is a submersion onto its image. So it goes from B cross N to M. Such that, so what it does is the following. For each element in B, it gives an embedding of N into M. And we call that N sub S, those embeddings. So this is one condition. And the second condition is that it should be submerged onto its image. Then we have the following lemma. Let's take another submanifold of M. We call it N tilde, so that its codimension is equal to the dimension of N. Then, if we integrate the number of intersections of NS and N tilde over B, that number gives as a lower bound for this up to a constant to the volume of N tilde. And this constant does not depend on N tilde. I mean, it depends on other things. For instance, it depends on psi, but it doesn't depend on N tilde. Okay, now we will apply Crofton's inequality into our setting. Lagrangian tomograph. So, like we call a map psi which satisfy these properties a Lagrangian tomograph. So now psi is going to be, so now L is going to be parameterized by a ball, the embeddings. Psi goes to a tubular neighborhood of L inside M. We want it to be a submersion onto its image. So we require that LS, the embeddings of L, are embedded Lagrangians for all S. We also want to control the Hofer distance between L sub S and L on the right hand side for all S. So I put some numbers here, delta and epsilon over 2. These are related to previous choices, epsilons, but here we just want to control this distance, make it small as we want. And one can do this, one can find such a tomograph. They exist, and here one can find a tomograph with D equal to 2 times dimension of L minus 1. This comes from like Whitney's theorem, immersion theorem. So like given an immersion of L into RD, R2 to D, one takes the component functions, then like linear combinations of, one takes those component functions, then linear combinations of those component functions, and then differentiate. That gives a psi, which is submersion onto its image. Then by shrinking the size of the ball, one can make sure that the second condition is satisfied as well. Okay, now how do we use this tomograph? So recall that this, we had that B epsilon L comma L to the Ki is bounded from below some constant times 2 to the Ki alpha for a sequence Ki going to infinity. This is by assumption. Now by Hofer stability of B epsilon, we get the second inequality because delta is less than epsilon over 2. This is fine. Now for the third inequality, so third inequality holds for almost all S in B. So because like since psi is a submersion for almost all S, L sub S is transverse to L to the Ki. So when we have transverse Lagrangians, intersection numbers are more than number of bars. Now we apply the Crofton's inequality. So we integrate number of intersections of LS and L to the Ki over B. So that gives an estimate, lower estimate for the volume of L to the Ki. And then up to a constant, then the volume of L to the Ki is more than 2 to the Ki alpha. We take the upper limit of the volume growth. That gives us a lower bound alpha. By Yomdin's theorem, alpha is less than topological entropy, and we are done. That's the proof of theorem A. And next, a sketch of the proof. Now I move to theorem B. Theorem B says that bar entropy is bounded from below topological entropy restricted to any locally maximal hyperbolic set. So step one is the algebraic part of the argument. So we say that a fixed point of phi is epsilon isolated if all Floer cylinders, these are solutions of the Floer equation that defines the differential in the complex. If all Floer cylinders asymptotic to x has energy at least epsilon. So you can think of this in the following way. In the action spectrum, in an epsilon neighborhood of the action of x, no other orbit is connected to x via the differential. Okay, this indeed tells us that, roughly speaking, it tells us that, roughly speaking, x is going to be an endpoint of a bar, either a finite bar or an infinite bar. This kind of tells us that that bar has length at least epsilon. So here is the lemma. Suppose that phi has p epsilon isolated fixed points, then b epsilon phi is at least p over 2. So for each such point, we get a bar of length more than epsilon, but if that bar is a finite bar, two ends might satisfy the same property, so we divide by 2. Now, a nice property, okay, we talked about this. So on locally maximal hyperbolic sets, topological entropy is equal to the periodic orbit growth rate. Now, if we combine this with the lemma, we arrive to the following. It suffices to find an epsilon k such that all periodic points contained in k are epsilon k isolated. Then we divide this number of periodic points by 2. That doesn't change the growth, and we will arrive to theorem B. So now we are trying to show that all points here, all periodic points here are epsilon k isolated. Now step 2 is a theorem by Basak and Viktor called crossing energy theorem. So for that, first we lift k to S1 cross n using the flow of phi and take an isolating neighborhood of k tilde there. We call it u tilde. Now there exists an epsilon such that all Floer cylinders that are asymptotic to a k periodic point contained in k and which are not contained in u tilde. So they're asymptotic to an orbit in the invariant set, but they leave this neighborhood u tilde. All such cylinders have energy at least epsilon. So here, the important thing is that this epsilon does not depend on the period of the orbit.
K tilde is just k times S1?
No.
What did you say?
For the S4,
you take the
S1
k and flow it.
Yes.
Can you say what k tilde is again, please?
So we take so we have a Hamiltonian diffeomorphism phi. We take a flow whose time one map is phi, and flow each point up to time 1.
Okay.
Sorry, could you please remind definition of isolating neighborhood?
So every point in the complement of the set k tilde leaves the neighborhood under iterations. But here, okay, I should say this. Here, there's a different definition. So this is an isolating neighborhood for the flow, not for the map phi. The definition is that every point in the complement of k tilde, u tilde, leaves this neighborhood under the flow, either in positive time or negative time.
Thank you.
One more thing,
so in particular, you don't have periodic points in u tilde that are not in k tilde, right?
Yes.
Why did you emphasize the independence of K here for the lower bound for the energy? Like, is it is it harder to achieve than just than a lower bound that decays with the period?
Yes, it is harder to achieve, to find a bound which is independent of K. And let me tell you why we need it. So we want to show that for every periodic point in K, we want to find an epsilon such that it works for every point. And in K, there are points of arbitrary period. So we need to find a lower bound that works for every period. And here it's harder to achieve, and actually, like without the assumption that the set is isolated, I mean, this is not true in the sense that one cannot find a global epsilon such that it would work for every K. But when you fix a K, one can always find such an epsilon. Let me also say this, like here, it is like here, hyperbolicity does not play any role. It's enough to have that the invariant set, compact invariant set is isolated. Now, this theorem handles cylinders that are contained in U tilde, that are not contained in U tilde. Next, we focus on cylinders that are contained in U tilde. Now, let me recall the following definition. So, a set in M parameterized by Zk is called an eta pseudo orbit of phi if it is almost an orbit of phi up to an error eta. Okay, now we're going to use Anosov closing lemma. For this lemma, it's important that K is hyperbolic and locally maximal. An application of Anosov closing lemma is this. So there exists an open neighborhood of K, an eta, and a delta such that all pseudo orbits, all such things that are contained in U are uniquely delta shadowed by a true orbit. So here uniqueness is important. So I try to say the same thing here again. So let's take an eta orbit that is eta pseudo orbit that is contained in U. Then there exists a unique periodic orbit in K such that the orbit like phi to the ix follows zi up to delta error. And this x is unique. Okay. Now we will use this lemma. Now let's take a cylinder, Floer cylinder, which is contained in U tilde. Now this is not the cylinder, I mean, you take a Floer cylinder whose lift is contained in U tilde. So since it is contained in U tilde, both limits are periodic orbits, both asymptotics are periodic orbits that are contained in K. Now, the first step is the following. If the energy of U is sufficiently small, then one can keep derivative of U with respect to S pointwise small. Then if this is small, then using the Floer equation, one can show that there exists an eta which is independent of K, such that the slices, by slice, I mean like we fix an R coordinate and look at the slice there. The integer points on the slices is an eta pseudo orbit for all S. So for this, we are using the Floer equation. Next, we apply closing lemma. We show that now closing lemma implies the following. If eta is sufficiently small, then this z hat S is shadowed by a unique periodic orbit in K. Now, So this W S depends continuously on S, and by uniqueness, we get that it's constant. At the same time, when S is close to negative infinity and positive infinity, we are close to the asymptotics of the Floer trajectory. From this, we get that the two ends of the cylinder are the same periodic orbits. And we are done. So the conclusion is that there exists an epsilon k such that if the lift of U is contained in U tilde, and if the energy of U is less than epsilon k, then U is constant. And this is the end. So I did it faster than I was. So this is the end of the presentation as well. Yeah. Thank you for listening.
Thank you. There is a question in the chat from Igor.
Is there?
I don't see it. Like,
no, there is no question.
oh, okay.
Okay, so maybe I have a question. So somehow there is this notion of slow entropy, which actually also was considered by Fraunfelder-Schlenk at some point. It's quite natural to consider in the context of Hamiltonian diffeomorphism. So the point is that you can look not only at the exponential growth, so that's something which topological entropy measures, but also, let's say, polynomial growth. Okay, and in principle, for Hamiltonian diffeomorphisms, at least of aspheric, symplectically aspherical manifolds, so certain quantities grow. So, for instance, norm of differentials often grow. You have certain non-trivial lower bound. And my question is whether you can grasp some quantity related to barcodes, which also necessarily grows.
I mean, I don't know. Like, we would need. I don't know. Like here, to say something about barcodes, we use this Anosov closing lemma to get a lower bound for the energy of cylinders. I mean, we would need something like that.
Mm-hmm.
I don't know. Like,
but that's for the estimate in one kind of direction, right? So closing lemma was used. I forgot, for theorem B, right? Not for
yes.
theorem. I see.
You want to bound from above?
I know. Well, I don't know. It was kind of, yeah.
Maybe I can chip in here. I think it's probably much easier. I think detecting polynomial growth is much easier than finding exponential, than seeing exponential growth.
Oh, but then polynomial should be universal. So I want polynomial growth in this language, so that for every Hamiltonian diffeomorphism, which is not the identity, you have this growth.
Probably yes, but this is a very different question. One of the it's an interesting question, I agree, but it's a different question because kind of this whole point of the project is that it's not universal.
Okay, no, that's understood. Okay.
That's something which sort of specific, it's sort of by design not robust.
Mm-hmm. Okay, thank you.
But what kind of growth could you have for, say, an irrational rotation of the sphere? I mean, the barcode is just 2 bars, no matter How many
No,
iterations?
no, but I mean on sphere you also don't have growth, right? So you have
You meant only spherical
torsion.
manifolds?
Let's say on a spherical manifold.
Okay.
Okay, and so then yeah, and then you know that let's say on surfaces you must have linear growth, yeah, on surfaces of higher genus. Okay, and so the question is whether you can formulate this in the language of course.
So can I ask a question? So you said so in higher dimensions you proved to us that barcode entropy is smaller than equal to topological entropy. Do you have any ideas whether it could coincide, or do you have examples where they don't coincide?
I don't know examples where they don't coincide, and for general, like in the paper, we conjecture that they do coincide, like C infinity generically, but I don't have much to say about this.
Okay, now a related question is, so is it possible that, I guess I think what you just told me answers my second question too, probably. I was wondering if it's possible to show in some examples, some interesting examples where, it's not known that topological entropy is positive or not, but you somehow show barcode entropy is positive. But it seems like probably the answer is you don't have any examples like that.
No. I mean, this barcode entropy definition, it's sort of a simple definition, but it's not that easy to work with. Like, it's not easy to show that it grows like under. I mean, this locally maximal set, that's the only thing that we have.
So basically, in all these cases where you prove it's, so it seems like the criteria you have for proving it's positive is basically criteria that come from dynamics, where it was already known that topological entropy is positive, right? Is that right? Or?
I mean, yes. So far, yes.
Okay. Now, Now there was this. You talked about the lower semi-continuity of your barcode entropy. So another question. You talked about lower semi-continuity of your barcode entropy in Hofer's metric. Now, barcodes are, I'm just wondering if barcodes are also continuous in gamma metric and also in C0 metric. Is it possible to prove its lower semi-continuity in C0 topology set?
So let me first say this, like we don't prove Hofer lower semi-continuity of the barcode entropy. Like in the relative case, we showed that like relative barcode entropy is lower semi-continuous in the Lagrangian.
Okay. All right.
And like by the result of Kislev and Shalukin, it would be also lower semi-continuous with respect to gamma naught, as it is in the Lagrangian. But that's it. Like,
okay. Thanks.
Sorry, and I missed. So in higher dimensions, do you have a counterexample where barcode entropy and topological entropy are different?
No.
Do you believe there should be such an example?
I mean, I believe that they are not always equal. Okay. And I agree that there should be an example, but I don't know.
But didn't you just tell me you conjecture that it is true?
C infinity generically.
Tricky.
Thank you.
Okay.
Okay, if there are no more questions, maybe we can thank Erman again.